Hello, everyone. Well, first off, congratulations to everyone who reached section 2.8. This is the end of the chapter. So one last. This is the last one and a really important one. Okay, so random samples. We've seen this idea come up a bunch of times, but now we're going to talk about it in more detail. So when you have a sequence of random variables, that come from the same distribution. And we're going to use the boldface symbol to describe the sample as a whole. Okay, but I used the word sample previously. When we said sample, we were talking about data, like observations from some experiment or observational study, like data. But here we're talking about, when I say random sample, I'm talking about n random variables. Okay, so notice the capital letter X. So it's not data, this is n random variables. Okay, and what can we tell about this random sample? Well, everything we did with ordinary samples, so with data, like the mean and the variance, we can do the same thing with the random sample. Now, the mean of a sample is a number. Okay, the mean of a random sample, so these are n random variables, so they're all over the place. They could take on any value. It's not the same variable repeated n times. It's like n different independent draws. So the possible values will vary all over the place. So this is also a random variable. The x bar, capital X bar, is a random variable. And then statistician came up with a very fancy name to describe this, the distribution of these the variables computed from random samples, call them the sampling distribution. Okay, what it means is that the distribution of the mean, for example, that you obtain from different random samples. So it's the sampling distribution. What you would obtain if you repeatedly sample. Anyway, it's the name of the thing. I'm not going to justify it. However, because it's such a complicated concept, you'll see it will take us like 20 pages to get to the point here. And normally all this information is shoved into a few paragraphs in the middle of a statistics explanation. And it goes, well, I had to read at least 3 books before I was like, oh shit, this is an important concept. Like to realize that this is actually the cornerstone of chapter 3, frequentist statistics. The classical statistics procedure are all derived from the knowledge of the sampling distributions, using their properties. But this is coming up in chapter 3. For here, we're still in probability land. So we're just setting up the mathematical model for that distribution. Okay. This whole section is about under the assumption of independent identically distributed. This is what that means. The joint distribution of the random sample is the product of n copies of the same distribution. Okay. We've seen a bunch of examples like this okay. So what is a statistic? Is any quantity you compute from a sample. We've seen a lot of those. Remember section 1.3, all of these quantities we computed are called statistics. In this section, we'll talk about the mean statistics. So everything applies to the other ones, but we'll focus on the mean. Here is some code for people who like code. But yeah, so the idea is you have the population, you have some sample, and you compute the mean of that sample. Nothing you haven't seen before. Here are some examples. We create a random variable z and we create samples of different sizes. Same from the exponential, and same from the uniform. Spoiler, when you compute samples that are larger and larger, the mean of the sample gets closer to the mean of the population. So this, kind of saw that in the previous section when we used simulation. Now we have a practical result that says that no, when you use a the random sample, the mean of the random sample will converge to the mean of the population. So this is not that exciting because we're building up to something even more exciting than this. Okay. So extremely important section. So if you understand this section, and you might need to reread it a couple of times, I told you it took me a while, then the chapter 3 of the book will be easy breezy, okay? And it's all in this picture. Okay, so we still have the population, which we model as some random variable. We take a sample of size n, but this is not a real sample. This is a hypothetical. You see, this is a capital X. So we're imagining taking a random sample from the population. So it's not a particular sample, it's like the process of, it's any possible random sample. And then we say, well, what is the mean of that hypothetical random sample? So that's a capital X bar. Well, that thing is called the sampling distribution of the mean. So capital X bar is a random variable. Its distribution, here is the notation, is the sampling distribution of the mean for the population fx for samples of size n. So it's quite a bit of a sentence to say that. Okay. Two approaches to the sampling distribution. There's a formula. Our approach, we'll talk about the formula later on. We start with a simulation. Okay, so this concept here, the sampling distribution, we obtain it by creating thousands of samples. So each of these is a sample of size n. Okay, and then for each sample we compute the mean of that sample. Then the histogram we obtain from this, that's the sampling distribution. Okay. First example, and this is, yeah, okay. Let's look at the pictures, you can read the text. So these are 10 samples from the uniform distribution. You see, all the blue dots are uniform between 0 and 1. And then the diamonds are the means computed from each sample. So the blue dots vary all over the place, but the diamonds seem to be always near the mean, near the middle of the graph. Okay, now imagine you take all these diamonds and you stack them, and then you plot a histogram to say like what are the, so this was 10 samples. In the code we switched to 1,000 samples. So this is the means of 1,000 different samples computed, and you get this distribution comes out. So this is the sampling distribution of the mean computed from samples of size 30 from the uniform distribution. Sorry, it's a long sentence, but there are three things I need to say. So it's the sampling distribution of what? Of the mean. And then you have to say what's the population, and then you have to say what sample size it is. So that when you cannot say it's the sampling distribution, you have to say the sampling distribution plus three qualifiers. So how big are the samples? What is the population, and what is the statistic? Okay. And here is the code for generating sampling distributions from any random variable. then we repeat the example using the standard normal. Interesting. Okay, so the population here is very different, but the sampling distribution came out again to be like a curve like this. That's cool. But you know, both of these are, the blue dots in this case and in the previous case are all like some distribution that goes all over the place. So it's normal that the means are have this shape, right? They have a same shape. But now we take a third example, the exponential distribution. So look at the blue dots. The blue dots have nothing to do, right? They're all, remember the exponential distribution is always concentrated near 0 and it drops off, okay? So it's definitely not symmetric left-right. It's just, it's completely skewed, okay? Yet, the mean we compute from each of these samples, they all seem to fall around here in the same place. When we draw the histogram, we still get a curve like this. Okay, so now we might be wondering, is this a coincidence, or how come the sampling, the means, the sampling distribution of the mean computed from 3 different variables, they all end up looking like a bell curve, like a Gaussian, like a normal distribution? Well, so nope, spoiler, it's not a coincidence. It's in fact a deep result in probability theory that if you take a random sample of size n from any distribution, from any random variable, the mean has to exist, the standard deviation has to exist. So there are like pathological cases where this doesn't work, but for most random variables, if you take a random sample of size n and you compute the mean of that sample, the sampling distribution of the mean is going to be a normal, a bell curve. So the theorem is true, so this becomes exactly true as the sample sizes grows to infinity. But even for finite sample sizes, it's approximately normal. Okay, and the mean of the sampling distribution is going to be around the mean of the population. So this was lambda 0.2, the mean, it was 5. So we see that it gets concentrated around 5. So that's part of the result. So the central limit theorem tells us 3 things. So first of all, the shape is normal. The mean of the sampling distribution is the population mean. So that's kind of intuitive. And the biggest new result is this part. It tells us actually a formula. The standard deviation of the sampling distribution is the standard deviation of the population and this scaling factor, square root of n, divided by square root of n. This formula is extremely cool because, for many reasons, chapter 3, I don't want to know spoilers. Here are some more graphics, which we will look at here. We talked about this. Central limit theorem. I thought I would be able to draw those separately, but anyway. Okay. This is not cleaner, but yeah. So a uniform random variable, and each panel shows samples of different sizes. Okay, so for samples of size 10, look, they're just, in each row there's just 10 blue dots. The mean is always going to be around 0.5, but you see that the means are the diamond shapes, they jump around a little bit, right? Because it's a very small sample size. The mean of 10 uniform numbers is some number, could fall anywhere here. When we jump to sample size 30, they still jump around, but less. And a sample size 100, you see that they're really concentrated near the mean. So if you remember, this is the behavior we expect. So the greater the sample size, the variability, the width of the sampling distribution of the mean, we expect it to get smaller and smaller. And this is exactly, so this is, imagine taking all those diamond shapes and plotting a histogram of them, but now for 1,000, I think. For 1,000 of them. This is the orange histogram is the sampling distribution of the mean from samples of size 10. And then the purple line is the prediction of the central limit theorem. And you see, it's a pretty good model, all right? So the central limit theorem, the purple line, each time, it's very close to to our simulation, okay? So we repeat the same thing for the standard normal. Again, small sample, medium sample, large sample. Variability is large, variability is medium, variability is small. Let's look at the histograms. Very good fit. And then one more time for the exponential distribution. Small sample, medium sample, large sample. So here, this is the most difficult case because the distribution is extremely skewed, right? The exponential, again. Let's see. So the skewness in the data results in skewness in the means, right? So you see it's not perfectly fitting. This part is higher here and there's a gap here. But when we get to samples of size 30, definitely samples of size 100, we're starting to see that the central limit theorem still is a good model for the sampling distribution of the mean. Okay, I let you play with those. Yeah. I don't know where I say this, but okay. The reason why we have statistics, the reason why statistics works. This is why we conclude this chapter, and it's a natural lead into into chapter 3. As you get larger and larger samples, the statistics you compute from the samples, you see, their variability starts to get really, really small. So when we get to the statistics chapter, we're going to do the inverse problem. We're going to look at a sample and try to guess what population it came from. So the larger the sample, the better our estimates of the population parameters are going to be. So we'll use the central limit theorem to compute all kinds of results, to give confidence intervals, to use hypothesis tests. You don't need to know any of this for now. It's just you need to know the math and the probability as a building block. We're going to see what we're going to use it in chapter 3. It's just saying, like, don't skip this section, make sure all the exercises, because yeah, this is kind of the cornerstone of this chapter. That's why we were building towards make sure you know you read section 2.8 in detail. All right, see y'all.